Yes.
I'm in France at INRIA in Paris.
Okay. So he's a researcher in the quantum information theory at INRIA Rocquenfort in the team secret, and he has obtained his PhD from Telecom Paris Tech in 2009. And his areas of research interests include quantum information, quantum error correction, and quantum cryptography, among many other things. Today, he is going to talk to us on his Ldpc course. Is that right, Dr. Anthony Leverrier? Yes. So over to Dr. Anthony Leverrier. It gives me great pleasure to be introducing you to this gathering today. Please take it away. Yes.
Yeah, thanks for the introduction. Thanks for inviting me. I'll try to share my slides. Do you see the slides now?
Yes.
And the pointer. Do you see the pointer?
Yes.
Okay. So thanks a lot. Thanks very much for this invitation. So today I want to talk to you about quantum error correcting codes and a special family of quantum codes called quantum Ldpc codes that have found like a lot of applications for quantum computing, and there's been a lot of exciting progress in the past few months about these codes. So we'll try to tell you a little bit about that. Okay, so but before I talk about quantum codes, let me introduce classical codes. Okay, in case you don't know about that. So the main setting is that you have some information, some bits that you want to send. And you have some noise on your channel. So the way you will proceed is by encoding your message into a longer message using redundancy. Okay, so the idea is that if you want to encode you want to send some bits, you won't send arbitrary bit strings, but what you will do, you will send bit strings like x1, x2, x3, xn that satisfy some constraints. And typically the constraints that you want, they are linear constraints. Okay, so maybe you will say, okay, x1 plus x2 plus x3, I fix this to be 0. I also ask that x3 plus x4 plus x6 equals 0. Okay, so I have like a bunch of linear constraints, and then the words that are allowed, the code words, they form what is called the code, and the code is just the kernel of some matrix. So it's just the solutions of some linear equation hx equals 0. Okay, so the code words, they are all the vectors x of length n, such that hx equals 0, where h is some parity check matrix, okay, that specifies all these equations. And if you do that, okay, you have a code of length n, that's the length of the code word, that can encode a certain number of bits. The number of bits it encodes is the dimension of this space. Usually we denote it by k. Now, if you have an error that occurs in the channel, so an error E, so your message x1 to xn is corrupted, and what you receive is x1 plus e1, x2 plus e2, xn plus en. What you can compute is called the syndrome of the error, and the syndrome is just you apply h to your vector e, or to the received vector x plus e, h of x equals 0, so you get he, which is called a syndrome. Okay, and from the syndrome, you will want to correct the errors. That's kind of the goal. And one of the parameters that is very important when you have a classical code is the distance of the code. Okay, the minimum weight of an error that you cannot detect. Okay, so it's the minimum Hamming weight of a code word which is different from 0. And usually what you want, you have these notations, you have length n, you have the dimension k, and you have the distance d. And what you want is that for a fixed n, you want to have k and d as large as possible. Okay, so k over n is called the rate of the code, how much information you can encode per bit that you will send. And d is the distance of the code. And then, okay, as I said, when you transmit information, you will have some noise, you will have some errors. And then the goal is to, recover the error, recover the message that you send. So, okay, so given some syndrome S that you observe, that you can observe at the output of the channel, you want to recover E of minimum weight, such that H times E equals S. Okay. So that's the decoding problem. And you have basically two regimes of interest in the literature. You have the adversarial errors. Okay, you want to understand what happens if some adversary tries to put some errors on your message and try to corrupt it. And then if you want to fight against this, you require codes with large distance. And probably the setting that is more important in practice is that of the random errors. Okay, so the errors, they're not put there by an adversary, but they are just random. And then in that case, it's not so important to have large D. What you want is a good, efficient decoder. Okay, so that's the general setting. And in the 60s, so until the 60s, nobody really knew how to decode general codes. In the 60s, in his PhD thesis, Gallagher, he invented a class of classical codes called Ldpc codes. So Ldpc just stands for low density parity check matrix. And these codes, they have this property that H, or the equations, the parity check equations that you have, they only involve a few number of bits, okay, a constant number of bits for each equation. Okay, so the graph that we had before between the bits and the checks, the parity checks, this is a sparse graph. Now you have, every equation only involves a constant number of bits, and every bit only appears in a constant number of equations. And this is very nice because when you have this, then you can exploit the sparsity of this graph to design very good decoders that work well in theory and in practice. And if you take just a random, parity check matrix, which is sparse, with a constant number of ones in every row and columns, then with high probability, you will get a good code. So you will get K, the rate that goes linearly with N, and the distance goes linearly with N, so that's good. And as I said, you get an efficient decoder because of this sparsity of the graph. And this has been very useful. And this is applied in Wi-Fi, in 5G. So these are codes that work very well. So they were discovered by Gallagher like 60 years ago, but then they were forgotten for 30 years and they were rediscovered in the 90s. So in the classical case, yeah, these are the really good codes that people use. But now in this talk, and in the field of quantum computing, what we care about is quantum codes. Okay, we want like the quantum generalization of this, because we want to protect information against noise when you want to do quantum computing or quantum communication. So the main difference between the classical and the quantum setting is really the types of errors. So in the classical setting, you have only one type of errors. You have bit flips. Okay, 0 goes to 1 and 1 goes to 0. In the quantum case, you have two types of errors. You have bit flips and you have phase flips. So the phase flips, they're just, the 0 state is sent to 0, so it's not changed, but the 1 state is sent to -1, so you had a phase. And this is typically quantum. This is purely quantum. So in the quantum case, we have two types of errors, and the way we want to deal with that is by defining a quantum code. And basically, a quantum code, as a first approximation, is given by two classical codes. Okay, so you have some Cx, which is the kernel of some matrix Hx, and you have a second code Cz, and that is the kernel of the matrix Hz. And the idea is that one of the codes, it will fight against bit flips, and the second code will fight against phase flips. But you cannot take these two codes arbitrarily. You have quantum mechanics. The way that these codes they appear in the construction, and they should be such that the constraints, the X-type constraints and the Z-type constraints, they should commute. Okay, so maybe let me show you this on this picture. So it's basically the same graph as we had before. So now the bits are replaced by qubits. So these are the black dots in the middle. And now we have two types of parity checks that will act on these qubits. So we have X checks that now correspond to product of poly X matrices. So this one, for instance, this X check is just a poly of sigma X polymatrix on this qubit, and this qubit. Or for instance, this one, this check is applies an X here, 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 and there. And the Z check, it will apply a poly Z on this qubit, this one, and that one. And what you want to enforce, what you need to enforce to get a quantum code, a valid quantum code, is that the X checks commute with the Z checks. Okay, so that's the real novelty in the quantum case. You cannot take two arbitrary classical codes. You need to take classical codes that commute in this sense. So the X checks and the Z checks commute. Or you can write this equivalently, saying that the parity check matrix Hx and the parity check matrix Hz, they satisfy this equation. So Hx times the transpose of Hz should be 0. And so if you can enforce this, and I will explain later how you can enforce this thing, then you get a quantum code that will encode, k logical qubits as before. So before we had k logical bits, now we encode k logical qubits. And basically the number of qubits that you encode is at least the total number of qubits that you have, n minus the number of checks. You can also define a distance of the code. So it will be the minimum between two distances, between the distance of the code that protects against X errors and the distance of the code that protects against phase errors. But now you have a subtlety when you define a distance. So for instance, the dx, the distance for the X errors, you want to compute the minimum weight of a word of Cx. But Cx contains, because of this equation, you can see that the code Cx, it contains basically all the Z checks. Okay, all these, they're called the generators of the code Z. They will satisfy all the constraints of Cx because of this, this equation here. But these checks, they don't affect the code words. They just act trivially on the code space, so we don't care about those. So really, when we compute the distance of a quantum code, we care about the distance of the minimum weight of an element of Cx that is not in the code CZ perp, okay, in the code spanned by the Z checks. And the same for DZ. Okay, and we have the same notation as in the classical case. We have, n qubits that encode k logical qubits, and you have a distance d. And as before, we want k and d to be as large as possible. And now we can again define this notion of LDPC, so low density parity check matrix. And this just asks that Hx and Hz, they are sparse matrices. In particular, if they are sparse matrices, then it means that the generators, the checks, the Z checks and the X checks, they should have like a constant size support. And it means that, these two codes, Cx and Cz, because Cx contains this subcode that contains, code words of constant weight, this classical code cannot be a good code. Okay? It cannot have a large minimum distance. That's constant minimum distance. Okay, so if you want to design good quantum Ldpc codes with a good distance for the quantum code for this D, you cannot use good classical codes to build these quantum codes. So I will get back to this later. Okay, and so you can design, for instance, this code, and if you design this code, what you get is what is called a STEAM code that has length 7, so it encodes 1 logical qubit into 7 physical qubits, and it has distance 3. So why do we care about this? Why do we care about quantum codes? And the main reason, at least for me and for many people, is to, if we want to build a quantum computer, and there's a lot of noise, and we want to fight this noise. We want to fight this noise to, be able to, compute and to perform useful algorithms. And, like 25 years ago, like one of the founding theorems in this whole field was proven. It's called the threshold theorem, and basically tells you that if you have a machine, a quantum processor, that is faulty. So every gate is a little bit faulty, but not too much. Okay, so the physical error rate, per gate is below some threshold, maybe 1%, maybe 0.1%. Then there's a way to use quantum codes together with this machine, with this noisy machine, to implement any quantum algorithm that you want. Okay, so the idea will be to replace, if you want to run Shor's algorithm, what you will do, you will, instead of running Shor's algorithm directly, what you will do, you will run Shor's algorithm on an encoded version of your qubits using quantum codes. And then even if there's noise in the machine, you will be still able to correct to compute the correct outcome of the Shor's algorithm. Okay, so how does that work? So the main strategy in that proof was to use code concatenation. Basically, you will use L levels, so a certain number of levels of this encoding scheme that I had before, the STEAM code. So basically, every qubit, first I replace them by 7 qubits as before. So I just use this STEAM code to replace every qubit by 7 qubits. And then each of the 7 qubits, I will again replace them by 7 qubits again, with the second application of the STEAM code. And I will do that L times. And why do I do that? Because if I do that for each level of encoding, the physical error rate that I observe will go down. Okay, so if I start with some physical error rate P, and I encode it once, then because the distance of this code is 3, it means that you need to do at least 2 errors to make an error that you will not be able to correct. Okay, if there's only 1 error occurring, because the distance between any 2 errors is 3, if you have only 1 error, then you can correct it. So the only way here things can go wrong is that you need to have 2 errors among the 7. Okay, so the virtual, the effective logical error rate in this step is not P anymore, it's P squared. And if you do it again, then the effective error rate will be P to the 4th. And then after L levels, the error rate will be like P to the 2 to the L. Okay, so it will be very, very small. And basically, if you want to run an algorithm that has T gates and M qubits, what you need to achieve, the error rate that you need to achieve is basically 1 over this number. And if you want to do that, you can compute, it's not complicated. You want this number P to the 2 to the L to be approximately equal to this. So you need only L equal to the log of 1 over epsilon levels. And if you compute the number of qubits that you need, the overhead in terms of qubits is not that much. Okay, you just need like the number of qubits that you need. So you started with M, you wanted M qubits, you want to run an algorithm on M qubits, M ideal qubits. But now what this theorem tells you is that you can, instead of that, you will run an algorithm on M times polylog of 1 over epsilon physical qubits that are noisy. Okay, so you get this polylogarithmic overhead, which is just this ratio. And the question is it the best that we can do? And okay, and tell you the story. So 15 years ago, I was a graduate student. It was my first conference. I was in Barcelona in Spain. And I heard someone talk. It was David Poulin, and he was the first person who, talked to me about quantum Ldpc codes. And so David was working on quantum error correction at the time. And what his message was that, code concatenation, so really the idea that we had before, is very bad from a coding point of view. It's terribly suboptimal. What we should do is to use better codes with constant rate. And for instance, quantum Ldpc codes. Okay, so I don't remember exactly all the details of the talk of David, but the main idea is that you want constant rate code. So you want to have a quantum code that encodes a constant number of the number of logical qubits that you encode should be linear in n, in the size of your computer. And if you do that, you can hope to remove this polylogarithmic factor in the overhead. Okay, you can reduce drastically the overhead for quantum fault tolerance. And really, if you want to do that, the tricky part is that, as in a classical case, so you want to correct errors as you do the algorithm. And the way you do that is by measuring some syndrome, similarly to the classical case. But here, when you measure the syndrome, you need a quantum circuit to do that, and the circuit will be itself, noisy. Okay, so because this circuit is noisy, and you want to have, a syndrome that is correct, the syndrome extraction circuit cannot be too large. And this forces you to use Ldpc codes. You want the parity checks to involve, just a constant number of qubits so that you can extract the syndrome very efficiently. Okay, so that's the basic message. That's the reason why we want quantum Ldpc codes. It's really because we want to be able to, improve the overhead of quantum computing, of fault-tolerant quantum computing. And this is one of the promising ways to do that. Okay, so now that was the motivation for studying quantum Ldpc codes. And now let me tell you about what is known about these quantum codes. And so one example is well known. So it's called the Topological Code of QIQT. So remember, so what do we want? We want to define X checks and Z checks of constant weight that should commute. And then the code will be the common eigenspace of all these checks. And the insight of QIQT back in the 90s was to find a place in mathematics where this commutation came automatically. Because if you try to do it by hand, it's not so easy to do. So you really need to have mathematical tools to find automatic ways to get this commuting between X checks and Z checks. And what QIQT realized is that if you take a torus like this, and you put a tiling on the torus, and you put the qubits on the edges, then what you can do, you can define two types of operators called the placket operators and the stars operators. So basically, a placket operators is for each placket on your tiling, you will just define the product of poly Z on the 4 qubits that are around the placket. And the star operators, they will be products of poly X on all the edges that are incident to a vertex. And what is kind of magical is that if you define this for everywhere in the torus, all the blue checks and the red operators, they will commute. Okay, so the two that I draw here, they commute because they don't overlap. Their support does not overlap. But then if I take this blue one together with the star operator on this vertex, then you can see that they will, their support will overlap twice on this edge and on this edge. So they will anti-commute twice, the operators, so they will commute. And you can check that this always works. And so if you do that, you define a quantum code, an Ldpc code, called the Topological Code, that is not too bad. So if you have n qubits, so you have n edges, what you can show is that the dimension of the code is 2. So it encodes 2 logical qubits. So that's not a lot, but okay, that's something. And the distance of the code is square root n. Again, basically the distance of this code, you can see it, it's just an operator that goes around the torus like this, or that goes around the torus like this. Okay. So from a coding point of view, these are not very great parameters. This k here, the dimension is 2 is constant. It's not proportional to n, and the distance here is square root n. It's not proportional to n. But still, this is today the leading approach to do fault-tolerant quantum computing. So this is the approach followed by IBM, Google, and many others. Okay. Yeah, so I really insist that. So that's the kind of the leading approach, even though the parameters are not that good. And what I want to kind of, advertise today is that maybe this is not the right thing that we should do. We should do something else. We should, change. Of course, we should use better quantum codes. to do fault-tolerant quantum computing. And we should use good quantum Ldpc codes. So maybe, yeah, what I want to say is that, so this code, the Tori code has been, invented 25 years ago. And since then, many people have developed very good techniques, very sophisticated techniques to do quantum fault tolerance with this kind of codes. So the techniques that have been developed, for not so good quantum codes, okay, with poor parameters. And this leads to a massive overhead for fault tolerance. So for instance, if you want to apply Shor's algorithm, if everything was perfect, you would need like a few thousand perfect qubits. But because everything is noisy, what you really need in practice is more like 10 to 100 million qubits. So the overhead, the cost of fault tolerance is that you should replace every logical qubits by maybe 1,000 to 10,000 physical qubits if you use the Tori code. And the question is, can we do much better than this? Can we use quantum Ldpc codes? Can we use better codes where this ratio, this cost will go down to maybe 10 or so? Okay, so that's kind of the thing I want to emphasize. I want to say, okay, let's maybe try to forget about the surface code and try to look for good quantum Ldpc codes first, and then develop the tools for doing fault tolerance with these codes. Okay, so what we want is we want good Ldpc codes. So this is what I will talk in the rest of this talk. We want efficient decoding because it's not enough to have a good quantum code. We want to be able to correct it. Okay, because when you do the algorithms, you have you encode everything in your code, and then you have noise that piles up very quickly, and so you need to be able to correct this noise as fast as it comes. So we need efficient decoding, and this we have very, very recent results. There were 3 papers on the arXiv last week that explain how to do that. And then we also need to understand how to perform logical gates, okay, how to really run the algorithm with this kind of encoding. And for this, we are still far from them. Okay, but in the rest of the talk, I really want to focus on this question, how to find good Ldpc codes. So first, okay, so one thing I didn't say, so Kitaev had this idea of using a torus to design a code. And actually, this idea is very general. You can replace the torus by any surface that you want. You can even go to higher dimension. You don't have to use a manifold of dimension 2. You can use a manifold of dimension whatever you want. And this will always give you codes. Okay, and then the question is, can we, so this is a very general toolbox to design quantum codes. Are these codes good or not? So all these constructions are called topological codes. All the code constructions that come from using manifolds and tilings of manifolds. So where you use constraints that are geometrically local in some dimension. But what is known now is that if you do that, the codes that you get, their parameters, they will be very constrained. Okay, so remember that we want k, the dimension, and d, the distance, to be both as large as possible, and ideally we would like both of them to be linear in n. And what is known is that this cannot occur with topological constructions in finite dimension. Okay, what we really need is to have some codes where you have interactions, you have qubits that interact, and that you cannot have only nearest neighbors interactions. You need long-range interactions for this to work, for this to get good quantum Ldpc codes. Okay, and the idea of quantum Ldpc is really to keep the sparsity of the Parity-check matrices, but to drop the geometric locality. Okay, you don't want to say, okay, neighboring qubits, they will be allowed to talk to each other, but you're not allowed to talk to distant qubits. If you want that, then this puts too much restriction on what you can do. So topological constructions alone don't seem very promising to get very good quantum Ldpc codes. Something that works very well in the classical case to design good codes is just to use random constructions. You say, okay, I take a random construction like this, just explain how you will do it. and you can show that with high probability you get something good. In the quantum case, it's not the case. If you want a good quantum Ldpc codes, we don't know how to really get it by purely random construction. So you need some structure. You need some structure to enforce the commutation between the X checks and the Z checks. Okay, so that's that's the kind of the key question. What kind of how much structure do we need to get good objects? If you put too much structure, like in these topological constructions, then you don't get optimal parameters. If you don't put enough structure, then you will not get a quantum code. Okay, and so the kind of what I want to say is that good quantum Ldpc codes, they exist. They've been discovered like 6 months ago. And so how do we get to that? How do we get those? So it will be a story in 2 acts. First, I will explain how to increase the dimension, and then I will explain how to increase the distance. Okay, so first part, how do we increase the rate, K over N? And then the idea was, so the idea was put forward by Tillich and Zemmour was 15 years ago. The idea was to generalize the toric code construction and to realize that, you know, a torus like this is really, it's really a product of 2 circles. Okay, it's a product of the red circle and the blue circle. Okay, if you have the blue circle going around the red circle, what you will draw is really a torus. And in some sense, in some well-defined sense, the toric code is really a product of 2 classical codes associated with 2 cycles. So if you have a cycle, you have a natural code that is associated to it, which is a repetition code. So basically, you put your constraints on the circle, you put the bits, if you want, on the edges, and you say that 2 neighboring edges, they should have the same value. And if you do that and you're around the circle, then all the bits should have the same value, and you get exactly the repetition code with 2 words, the all 0 word and the all 1 word. And so okay, so to a circle, you can associate the repetition code. And if you take the product of 2 repetition codes, what you get is really the toric code. And then the idea of Tillich and Zemmour was to say, okay, now what if we kind of generalize this product of codes and take the product of 2 arbitrary classical codes? And what you get is really a quantum code. So these quantum codes are now known as hypergraph product codes. So the idea is that if you take 2 classical Ldpc codes, what you will get is a quantum Ldpc code. And in particular, if you start with 2 good Ldpc codes, so where K and D, the dimension and the distance, are both linear in N, which is easy to do in the classical case, then you will get a quantum Ldpc code where the dimension now is linear in N, and the distance is proportional to the square root of N. So the distance is basically the same as the toric code, proportional to the square root of N. But now the dimension has increased a lot. For the toric code, it was 2, and now it's something linear in N. Okay, so you get constant rate. So this was the first kind of breakthrough in this field after the invention of the toric code. And already these code constructions, they are very important, and they give you very strong results if you want to do quantum fault tolerance, because of a theorem of, a theorem of Gottesman, 2013, where he showed that if you have quantum Ldpc codes with dimension linear in N and distance not too bad, so you just need distance that is N to the alpha for some positive alpha, then you can, and if you have a very good decoder for this code, then you can do quantum fault tolerance with constant overhead. So this answers positively the question raised by David Poulin 15 years ago. So you can really use quantum Ldpc codes, so this kind of quantum Ldpc codes, so hypergraph product codes of 2 classical codes, and a specific decoding algorithm to have quantum fault tolerance with constant overhead. So this is already really quite good. but now the question is, okay, can we do even better? Can we improve the distance of these quantum codes? Okay, now we are kind of stuck with square root n for the distance. Can we do better than this? And if we could, then probably you can improve the threshold for the. You can you will be able to tolerate more noise on your quantum computer. Everything should be even better. You will need less redundancy, so you will need a lower overhead. So okay, so that's a big question. Can we improve? Can we find even better codes? Okay, so the question is really, can we find codes with distance bigger than square root n? And this was an open question for a long, long time, more than 20 years. Nobody knew how to break this barrier of square root n. And I think nobody knew whether it was possible or not. Even it was not so easy to find ideas of possible constructions that would beat this bound. And okay, what I want to say in this slide is the code construction that I just gave, the hypergraph product code. So it's really the product of two codes, of two classical codes, the red one and the blue one. And the way that the code is defined, you have basically many, you have your qubits that are here, and the way the code is defined is by putting many slices of qubits. You have two different types of slices, the vertical ones that will correspond to this code CA, and the horizontal ones that will correspond to the code CB. So in the quantum code, what you will really get is you have many copies of the two classical codes that you started with. And because any code word of the classical codes, they will give you like also a logical operator for the quantum code. Basically, you cannot beat, the distance of the classical code will be an upper bound on the distance of the quantum code. And that's kind of the reason why with this kind of construction, we cannot beat the bound, that the distance is upper bounded by the square root of the number of qubits. Okay, so if we want to beat this, we need like new ideas, and basically we need to change this kind of product. Okay, and this is what has been done very recently. Okay, so this is now the second part, so how to increase the distance. And maybe, yeah, what I want to say is like to do a quick overview of the progress in this field. So, and the progress was very slow for a long time. So as I said before, so in 1997, QIQT invented the toric code with a distance of square root n. So it's very simple. The construction is quite simple once you understand it. A few years later, these people they came up with a very complicated construction, topological construction that beats this bound, but not by much. Square root n times log n to the 1/4. So it's very, very small improvement. And then basically for 20 years, nothing happened. People were looking for better codes, but nobody found anything. And then, 2 years ago, there were a couple of papers that improved a little bit on this, using ideas from high-dimensional expansions, so very complicated mathematical objects that cannot generalize graphs. And the improvement that they got was very tiny. Okay, they just improved the exponent in the logarithm, factor. So it was still basically square root n times something. And then a bit later in the same year, Hastings, Ha, and O'Donnell, they came up with a very fantastic idea to break the square root n bound. And so they managed to get n to the 0.6. And then again, a few months later, Panteleev and Kalechev, they even got higher. So they got distance, which was almost linear in n, so n divided by log n. But for this cause, the dimension is very small. K is just logarithmic in n, whereas we want k linear in n. So this was like a bit more than 1 year ago, and then 6 months ago, the same two people, Panteleev and Kalechev, they managed to get good quantum codes. So good quantum Ldpc codes. So the distance is linear in n, and the dimension k is also linear in n. And in that paper, they also developed the corollary, a simple corollary of their construction was to, get classical codes, which are very interesting also, called locally testable codes. And there was another paper on the same day that did that, not the quantum part, but the classical part. So this was 6 months ago, and now we have a bit more constructions. So together with Gilles Zemmour, we developed a variant of this Poulin and KHF construction that also gives good quantum Ldpc codes. And we have like several classical locally testable codes. But okay, so what's the key idea to break this square root n barrier? And so if you recall, like a few slides ago, I was saying that when you do the hypergraph product code construction, what you get at the end is the quantum code that you get is really, you have many copies of the classical code. And basically, if you have like a logical operator for the classical code, it will be a logical operator for the quantum code. But now the quantum code is much larger because it has its size is the square of the size of the classical code. So basically, the idea to kind of improve on that is to take like more complicated product, not just like direct product, like just this line times this line, but what you really want is to have complete slices if you want. So you want the red thing to correspond to a classical product, to a classical code, and the blue thing also to correspond to classical code. And now you want the vertical axis to be very, very, very large compared to this thing. So you want n to be very large and delta to be constant. And if you can do that, you can get a good code. But then you need some structure to kind of define this kind of product. So this is exactly the picture that happens for the quantum Taylor codes that we designed with Gilles Zemmour. And so, yeah, so all the techniques so there were a few papers improving on the square root n bound, and they kind of use very related techniques to build this bound. And the main idea is to have like a more general notion of product. You have a product that with a third dimension, this vertical axis that I drew before. Okay, so I mean, and the code construction, they come in different names: twisted product for the first asyncs out, and then lifted product for Poulin and KHF. Balanced product from Breukman and Eberhardt, and probably so this is the kind of the right notion from topology that kind of encompasses all these other constructions. So now we have kind of a mess, many things, many possibilities for quantum codes, and a very nice website if you want to take a look if you're interested in the topic. This zoo, error correction zoo, gives you like a list of all classical and quantum codes that are known and their properties. So if you're really interested in the topic, you should take a look at this website. So I won't explain in detail the construction for these good codes. Just, yeah, I mean, we have the theorem that we have is something like this. We need two things when we make this kind of codes. We need small classical codes of length constant size, of size delta, which is a constant. And we need like a combinatorial object that corresponds to this complicated product. So this combinatorial object is called a left-right KLA complex. And we can show that it exists. And then you need small codes, and you can say that, okay, the small codes, we don't really know how to find them explicitly, but if you take random small codes, it will be good enough. You will get good quantum codes. Okay, so now what we have is that we have quantum Ldpc codes of length n with some distance which is linear in n. And the rate also, the rate k over n can be an arbitrary constant. And as I mentioned a few minutes ago, since last week, so last week there were 3 papers to define efficient decoding algorithms for these quantum codes. Okay, so now we have the quantum codes, these good quantum Ldpc codes, and now we have efficient decoding algorithms to, if you're given an error of weight linear in n, then we know how to correct it efficiently. We have decoding algorithms that are that take linear time to decode and to correct the errors. So that's really, yeah. So it's just last week. So we tried to coordinate to. We are coordinating with the authors of the third paper to put our paper on the archive on the same day, but somehow we got scooped a little bit by these researchers who put their paper first. So they put theirs first, and then we put our paper. And all the three constructions, the three decoders, they use the same kind of techniques. They use the same ideas. Okay, so that's I guess my final slide. What I wanted to say in this talk is that people have been developing ideas for doing quantum fault tolerance. You want to do quantum algorithm with faulty hardware, and you still want to do it exactly. So you need ideas from quantum error correction to do that. For more than 20 years, people were using, when they try to do that, to design schemes to do it, they were always using toric code or cousins of the toric code, which have very bad parameters in terms of coding theory. Distance is bounded by this, the dimension is constant. But since last December, we know that good quantum Ldpc codes exist. So we can have both the dimension and distance linear in n. And so the idea now is really to understand whether we can use these codes to improve the schemes for doing quantum fault tolerance. What we need to do is to find even better quantum Ldpc codes with efficient decoders and probably of small size. Okay, the codes that we have now, the results are asymptotic results. We know that if the code is large enough, then the distance and the dimension will be linear in n. But if you take a small instance, they will typically not be so good. So we really need to improve on that. And we need to better understand how to perform logical gates on this kind of codes. And of course, the challenge for experimentalists is to try to implement these things. Because now, as I said, the difference between these quantum Ldpc codes and the toric code is that you need long-range interactions. So maybe if you use supraconnecting qubits, it's not so good. But if you use, trapped ions, or if you use photons, or if you use Rydberg atoms, then it's possible to implement these long-range interactions. So then it should be possible to implement these quantum Ldpc codes. And that's what I wanted to say. So thanks for your attention. And if you have any question, please don't hesitate.
Leverrier, and there are, for a very informative talk, there are quite a few questions in the chat box. So the first one is, are hypercubes useful to get efficient decoding algorithm? That is the first question.
So I'm not sure what it means, hypercubes, in this context.
Maybe the person who has asked the question, Nitin Rath.
Or maybe I can go through the other questions in the meantime, if you want.
Okay, so the next question is, do all the quantum Ldpc codes outperform their classical counterparts?
So it's a good question. So it's not clear. So no. So in general, it's more complicated to design a quantum Ldpc code. So for classical Ldpc codes, we know how to get optimal classical Ldpc codes with optimal parameters for the distance and dimension. In the quantum case, we're not there yet. So now we have good quantum codes, meaning that dimension and distance are both linear in n, but the proportionally, if you look at the constants in front, they're not so good yet. So at the moment, no. At the moment, the quantum Ldpc codes are not better than the classical codes.
Okay, the next question for you is how the CSS codes are different from the families of Ldpc codes?
Yeah, so I would say that, so there are kind of two things. So the CSS codes, all the codes I was talking about today, they are all CSS. So CSS just means that you have two types of checks, parity checks. You have Z type and X type, and you don't mix up the Z and the X. But in general, you don't need to do that. So you could have more general quantum codes that don't do that. And in general, when you have CSS code, you don't assume anything about the sparsity of the constraints. So if you don't require that the constraints are sparse, that each check only acts non-trivially on a constant number of qubits, then it's easy to show by probabilistic arguments that you can get very good optimal CSS codes. Okay, really, the difficulty is when you want to enforce this additional constraint that the checks, they should be sparse. They should act on a constant number of qubits. So in this sense, if you want the Ldpc codes, they can be understood as a subset of the CSS codes with more constraints. So it's harder to get good Ldpc codes than good CSS codes.
Then the next question for you is how do the Ldpc codes reduce the required overhead for fault-tolerant quantum computing?
Yeah, so really the idea is that you have like a much increased dimension for these codes. You can encode many logical qubits into the same number of physical qubits. Okay, compared to the concatenated codes that I had before, or even to the toric code. The toric code only encodes 2 qubits, so you have 2 qubits within n. And so if you want to do a quantum algorithm with the toric code, you will need several patches of n qubits. So really the key to reduce the overhead is not the Ldpc constraint, it's really to use code of constant rates. You want a code that encodes many logical qubits within a certain number of physical qubits. And then the Ldpc constraint comes because if you try to do that and you try to read the syndrome efficiently, then you need this Ldpc condition.
The next question for you is there any efficient way to find a good family of Ldpc codes which are easily decodable?
Yeah, well, we don't know yet. So that's a good question. So right now we don't have that many families of good Ldpc codes. We have the one by Poulin and Kayachev, and we have the ones in our work with Gilles Zemmour, but they are related. So ours can be seen as a simplification of this family. So essentially, we have one main way to construct good quantum Ldpc codes at the moment. So for these codes, now we know how to decode them. But in general, for the moment, we don't really know how to design other quantum Ldpc codes that are good. And we don't know whether it will be easy or not to decode, to correct the errors in that case.
Okay, you have one more question. Is there any Ldpc code which is compatible with continuous variable systems?
That's a very good question. So it depends what you mean by continuous variable systems. So at the moment, there are kind of two very nice approaches to reduce the overhead if you want to do quantum fault tolerance. So one is the Ldpc approach that I mentioned. The other approach that is very popular is to use bosonic codes. Okay, so the idea is that you don't want to take your qubits to be from like a two-level systems. Rather, what you want to do is to take your qubits that is defined as a two-dimensional subspace of a Fock space. Okay, so you take a continuous variable system if you want. You have a bosonic mode, and then you can choose like a good two-dimensional subspace in this. So there are things called the CAD codes or the GKP codes that people are investigating, and then this should also lead to a very strong reduction in terms of overhead. So this is a very popular approach. And it should be possible to combine both approaches. And this is, of course, something that people want to do.
पूरा सही में gold mine ही मिल गया भाई.
Okay, so I think that will be all. Thank you very much for a very interesting talk and presenting something that you have just finished doing yesterday. Thank you very much once again. Let us thank Dr. Anthony Leverrier.
Thanks a lot for the invitation.
Thank you very much.
Thank you. So stop sharing.